Hi everyone, I'm Chris and welcome back to the lecture on linear regression of this machine learning course. This section is about data preprocessing. Data typically needs to be preprocessed before a model can be trained with that data. At first, we will take a look on data normalization. A gradient-based minimization is one of the most common approaches to train a model. But this approach is very sensitive to the scales of the independent variables. Here, a simplified illustration of a cost function by its control lines is sketched. These are lines of constant height of the function. Different scales of the independent variables lead to more ellipsoidal-shaped control lines. The gradient is perpendicular to the control lines, as seen in the previous section. So the ellipsoidal shape leads to gradients which oscillate their direction in the minimization. If the independent variables are on a similar scale, the minimization is much smoother. The control lines are more circularly shaped. So the minimizations go more directly towards the minimum. Of course, this is a simplified illustration of a nice smooth cost function. But it is most often beneficial to normalize the variables somehow if a gradient-based minimization is used. There are two very often used approaches to normalize a variable x1. The first is called min-max normalization. The values are scaled to fit into the interval of 0 to 1. The variable's minimum and its maximum need to be determined. Then, from all values of this particular variable x1, the minimum is subtracted. After that, the results are divided by the difference of maximum and minimum. So you can check if you put the max value for x into the equation, you get 1. And for the minimum value, you get 0. The other normalization method is standardization. The values of the variable are shifted and scaled to satisfy a standard normal distribution with mean 0 and standard deviation 1. So therefore, you need to subtract the mean of the variable and divide by the standard deviation. Another common step in data preprocessing is to remove outliers. Outliers are data points with values far from most other data points. There are several reasons why you should consider to remove such outliers. First, because these data points might be corrupt. For example, someone mixed up with the units and gave a price in cent instead of dollar. Another reason to remove outliers can be that the data might be okay, but you want to restrict your model to a certain value range where you have enough data to ensure a good model quality. To check your data for outliers, you can either check value ranges directly or you can use statistics. A statistical approach can check for outliers in a variable, for example by using box plots. At first, plot your data for one of the variables on a vertical axis. As sketched on the right side, here we choose the variable x1. A box plot is basically a box with a length that includes the middle 50% of the data values in your dataset. So 25% of the data are values greater than the upper bound of the box. The other 25% are smaller than the lower bound of the box. The median value is highlighted within the box. The median is the middle value, so 50% are below or above this value. The length of the box is called interquartile range. Above and below the box are the so-called whiskers. They contain all data within 1.5 times the interquartile range. The factor 1.5 can be adjusted if you want. Typically, all data points above the upper whisker and below the lower whisker are called outliers. So you can identify these outliers using box plots, and you can remove them if you want. Besides checking the data for outliers, another step in preprocessing the data is to handle missing data values. If there are missing values in your dataset, you often need to preprocess them before you can use your data for training your algorithm. One simple option is to drop samples with missing values in your dataset. Such a sample is a row in the data table. Another option to treat missing values is to impute them. This can be done by simple approaches, like the mean or the median of the other values of the variables. But also more complex models to estimate missing values can be used. However, at this point, we will not go further into the details of such approaches. It can be beneficial to apply a variable transformation to the independent variables of the dataset prior to the modeling. Here, at first, we consider numeric input variables. These are variables with real numbers. A variable transformation can be a simple functional modification. For example, the input variable x can be transformed into x squared or the sign of x. Further, we can combine different variables. Consider, for example, a real estate price estimation with given variables length and width of the house. An interesting new feature would be the corresponding area, length times width. The house price might be much more related to this area, and so it is beneficial to incorporate this new feature. So the algorithm can learn the functional relation much more easily. This is especially important if only a small dataset is available. Besides the combination of different input variables, there are further possibilities to incorporate your knowledge about a system. For example, you could add the calculation results of complex simulations as additional input features. So far, we considered mostly numerical features. But let's reconsider our real estate price estimation. What about a feature like has the house a lake view? We would assume that if this categorical variable is yes, then the house price is much higher. But how can we incorporate such a variable? Categorical variables need to be transferred to numeric values to be processed by a machine learning algorithm. Such a categorical variable can have values such as yes and no. We could simply transfer each category to a numeric value. For instance, a yes can be a 1 and a no can be a 0. If we have more categories like A, B and C, we could use a 1 for A, a 2 for B and a 3 for C. For example, the measurements A, B, A, C will then transfer to 1, 1, 1, 2, 1, 3, 3. However, This is not the best way for transformation. Usually, the distance between A and B is not equal to the distance of B and C. For example, the categories can be small, medium and large. With 1, 2 and 3 as replacement, the algorithm might assume that there exists a metric and distance relation between the classes, but we don't really know that from the data. In that case, it is better to use binary variables. These are variables with just two values, 0 and 1. Reconsider our example with A, B and C. A first variable could be A or not A as 0 or 1. Another variable can be B or not B. And a last one similar for C or not C. Our series AAA, B, A, C, C, C leads then to three new series. The first represents A or not A. This gives 1, 1, 1, 0, 1, 0, 0, 0. In a similar way, you can get the other transformed variables. Such a variable transformation is also one-hot encoding. Note that variables with only two values don't have distance relations. Section finished. Thank you very much for listening. If you like this video, please click the like button and consider to subscribe the channel. If you have any comments or questions, please leave a comment down below. And thanks again for listening. See you in the next section.